Okay, so we have to solve this. Um, so we need to check first this differential equation if it's exact. So this is our P. This is in the form of um, PDX. So this is our P. This is our Q. Uh, this is in the form of PDX plus QDY equals 0. And we need to check if this is exact. So if dp over dy equals dq over dx, then exact. So let's go ahead and do that. So dp over dy is the partial derivative of p with respect to y. So 2x is a number, stays 2x, e to the 3y times the chain rule on the 3y. So that's 3 plus the derivative of e to the x with respect to y is 0. And then let's do dq over dx. So dq over dx is the derivative with respect to the x. E to the 3y stays e to the 3y. 3x squared becomes 6x. And y squared is 0. So as we can see, because this guy is 6x e to the 3y, they are indeed equal. So dp over dy is equal to dq over dx, and therefore differential equation is exact. Now, once the differential equation is exact, we know that there is an f function of x comma y where there exists some function of x comma y where df over dx equals p and df over dy equals q. We can take either one of these two and solve for f because we know what p is. So let's do that. Let's take the x. So df over dx has to equal our p. P is 2x e to the 3y plus ex. And our objective is to solve for x. So multiply both sides of this equation by dx. So we get df is equal to 2x e to the 3y plus ex dx. And now what we can do is we can integrate both sides and we get f to equal, sorry, this is a y here. Okay, well, y is constant, so this is just, it can come outside the integral. This is just the integral of 2x dx plus e to the x dx. So f would be e to the 3y times x squared. The integral of 2x is x squared, and the integral of e to the x is e to the x. Okay, and now our constant of integration is, because this is a function of two variables x and y, we are integrating with respect to x. So our constant of integration is a function of the other variable that we are not integrating with respect to, which is, let's just call it hy. And now the objective is to figure out what this hy is. So now the question is, what's hy? And here we're going to go and differentiate this one more time with respect to y. And we're going to set it equal to df over dy, which is q, which we have, and solve for h of 1. So if I differentiate this with respect to y, This is just 3x squared e to the 3y, partial with respect to y. E to the x is 0 because there is no y, and h of y is just dh over dy. And this has to equal my q, because df over dy is also q, as we said here. And q is 3x squared. So that means 3x squared e to the 3y plus dh over dy is equal to q, which is 3x squared e to the 3y minus y squared. These two guys cancel out, and we have dh over dy equal minus y squared. Separate the variables. Dh equals minus y squared dy. We integrate both sides. And then we solve for h. H of y is just minus y cubed over 3 minus y cubed over 3 plus some constant c. So I take this back and plug it into my equation A, and this would be my f. Plug in A, and so we have f equals x squared e to the 3y plus e to the x minus y cubed over 3 plus c. And one of the requirements for this method to work is that f of x comma y equal to some constant c, another constant c. So I can remove this f, plug in another c, and then add the c's together to make one c. So I can make this, let's say, a c prime, and c prime and c will just add to another c, and my final answer will look x squared e to the 3y plus e to the x minus y cubed over 3 is equal c prime minus c, which is just another constant c. So this would be the solution of the differential